Okay, so this talk is about deep embedding forest. It's a collaboration with my co-authors in the list. Unfortunately, Jay couldn't make it due to the visa issue. And I think my manager, JC Mao, is in the audience. And we are from a newly formed AI and research group from Microsoft, most of us. And Halako is from the UCSC. This is the agenda I'm going to walk you through. Our motivation is to build web-scale models for applications such as web search and online advertising. And these applications usually have billions of samples with multiple heterogeneous features, hundreds of thousands to millions of dimensions. And depending on the applications, they have various types of objective functions, including regression, classification, ranking, and so on. And usually, the serving has to be real time. So this work is in the context of Bing ads. When a query is sent to the Bing search engine, we return ads from time to time along with the organic results. And the ads will have ad title, ad descriptions. And the leading keywords is the key information to connect query and ad. And a click on an ad will lead to the landing page. So the central problem is to give a query how likely a user will click on an ad. And this is the model we use to demonstrate our work. So a common approach is to manually create so-called combinatorial features defined in the joint space of individual features. And these features sometimes are called cross features. And then you feed these features into the trainer of your choice. And that's what usually people do. Well, the challenge is what and how many features to cross. Right? You want to cross query with ad title, query with descriptions, or you want to cross all of them. And this is where our scientists and engineers spend most time on. These features are very expensive to create, to maintain, and to improve. And they're also very hard to get help from others, because before they can help you, you have to learn the domain knowledge first. So in KDD 2016, we introduced the deep crossing to solve this problem. The key idea is to use the raw feature as raw as possible and let deep neural network taking care of the rest. And we know the same strategy worked for image and speech recognition. Now the model has been applied to both problem of adequate prediction and web ranking. And it's scaled well offline with offline training with billions of samples, and demonstrate significant gains as compared with our production model, which we know are hard to beat. So this is to give you a brief summary of the deep crossing-alike models proposed around and after deep crossing. The neural factorization machine proposed to use a bi-interaction pooling layer instead of the stacking layer. And they demonstrate that it's useful when dealing with small training sets. And the deep interest network proposed to add extra embedding layers to cross feature groups of different nature. And in each case, the layers inside the green boxes are the denser fully connected layers. We'll come back to this point later. And there is also wide and deep net model for apps recommendation, and the DNN model for video recommendation, both from Google guys. And the latter fuses multi-module information from video and text using a similar architecture. And you can take a look at the paper Deep and Crossing Network at KDD this year if you are interested in a comparison of some of these models. But keeping in mind that all these experiments with different data at different scales, sometimes the solution and problem are very different. So while these models help with feature engineering, especially to generate cross features automatically, they all face the same challenge that the dense layers are too slow for real-time serving. And to meet the challenge, we propose a model called the Deep Embedding Forest, DEF in short. When you look at the model architecture on the left side, the part below the stacking layer is exactly the same as the deep processing model. And so is the objective function. The only difference is that the layer above the stacking layer is a forest tree-like layer, fully integrated with the rest of the network. Here's how we build DEF. In the first step, we train a deep processing model as usual. And in the second step, we use the trained stacking layer as an input feature and the same objective function to train a forest model. And in the third step, we use the embedding models in the first step to initialize the parameters of the embedding layers in the DEF model. And we do the same thing for the forest layers, using the forest model in the second step. Then we apply the joint optimization algorithm called partial classification to do a back-forth propagation. And there are two algorithms to build DEF actually. The first is called two-step DEF, which simply combines the embedding and stacking layers from the first step with the first layer from the second step. And the second algorithm called three-step algorithm on the right is on top of the initialization, the first two steps of initialization, it does a partial classification algorithm. Basically, propagating the arrow back and forth between the forest layer and the embedding layer. So now, let's take a close look at what we meant by partial classification. On the top is the stacking layer with all the features. And the lower part is the forest model. In this case, we only show one tree for the purpose of illustration. And like all the tree models, it has decision nodes, it has routing probabilities, class distribution at leaf nodes, and also output score. Now, two things to call out here is that the routing probability in this case is a function of a single feature in the stacking layer. And the output score is the sum of class probabilities on all leaves through all paths. Now, as compared with deep neural decision forests, DNDFs, which represents a class of full classification algorithms. It also has decision nodes, also has class distribution at the leaf node, but the routing probability is a function of all features in the stacking layer. So you can imagine that it runs much slower than partial classification. Now looking back on the two-step DEF, the routing property is the same as the partial classification. But the output score is a class probability through a single pass. So you can imagine that the two-step DEF is faster than the partial classification and is much faster than the full classification. For experiments, we use as input feature a heterogeneous feature of 150,000 dimensions, and we use log loss as an object function. For models, we train a deep processing model with GPU cluster powered by CNTK, and the deep processing model has one embedding layer for each feature group, one stacking layer, 4 deep layers, and one storing layer. For forest-based model, We use both light GBM and XGBoost, but we rely mostly on light GBM because internally we have a distributed light GBM setup on CPU cluster. For DEF training, the partial certification is implemented on GPU cluster with CNTK. And it has one embedding layer for each feature group, one stacking layer, and one forest layer, and one storing layer. So the features, these are the examples of individual features. We convert query to query the keywords and the title, all these textual features into a trilogram, and we use one hot features for features like match type, campaign ID, and so on. And we also use counting features, dense counting features for things like campaign ID count. And this is what we meant by heterogeneous features. So it can be sparse, both sparse and dense, textual and categorical, and also counting features. So the first result is with 3 million samples using one thread. We compare both log loss and the prediction time for 3 algorithms, including deep crossing, 2-step DEF, and 3-step DEF. And for the 2-step DEF and for 3-step DEFs, we use light GBM. And you can see from the table that the 2-step DEF reduces prediction time by 10x, with a slight improvement in log loss. And 3-step DEF improves log loss, again, when you compare with the 2-step DEF, but it's slow. We didn't report the prediction time for 3-step DEF because it was implemented on the GPU cluster, so it's not an apple-to-apple comparison. This is a prediction time versus number of threads. So the prediction time for DES reduced further as the number of threads increased. And you can see the same pattern is shared by XGBoost and the light GBM-based model. In contrast, the deep crossing model reached the peak performance at 5 threads. And this is because when the communication cost picks up and outweighs the parallelism. So the prediction time actually goes up when the number of threads increases. We also did experiments with 60 million and 1 billion samples. In this case, partial certification is too slow, so we only report the results from deep crossing and 2-step DEF. Again, we report both log loss and the prediction time. And you can see the reduction in prediction time is consistently observed. Talking about the effect of scale, the table shows that the comparison between the deep crossing and 2-step DEF with a sample set of different scales, from 3 million to 1 billion. And if you look at the scores, the log loss decreased as the number of samples increased. While DEF trained with 1 billion samples performs worse than deep crossing, it is still better than deep crossing trained with 60 million samples. So that's why the design goal of DEF aims at the scale for billions of samples. So what can DEF help you? One scenario is that if you're building a model from scratch for a new application domain, then you can build a high-performance model with a fraction of effort, and the scale can be sometimes many years versus several months, a few months. And of course, if you're looking for new directions to improve an existing model, the chances that DEF can give you some significant boost in performance, as demonstrated in our experiments. And the best scenario is that you already have invested in the forest and the tree-based serving, and then you don't have to buy GPU and FPGA. You just train the deep learning model and then plug in the features. Plug the feature into that serving stack, and to conclude, DEF combines the best of deep processing-like models and forest tree-based models. It has a building mechanism to handle high-dimensional heterogeneous features. And through deep processing embedding and fast online serving through the forest and tree layer. And it also is compatible with existing forest tree-based serving stack. In the end, I want to have a brief introduction of our team. I just highlight the part that I feel relevant. So we are a multi-billion-dollar business for Microsoft, and we do machine learning, deep learning, text and image mining, among many other things. And there are several hundreds of us under my manager, Jason Mao. And we have also data and applied scientists and machine learning scientists. Every day we are getting terabytes of data from billions of edit impressions. And we do data analysis, we build models, and we serve high volume user queries with all kinds of platforms, including Azure Cloud, GPU cluster. And we are always looking for top talents at all levels to join our team to meet these challenges and make impact together. So feel free to take picture of this slide and reach out to us through LinkedIn or whatever channel you have. Thank you very much.